So let's move to the Einstein's idea. Okay, before doing that, so we are having the curvature tensor. So this, what it is? Let's say A, B, C, D. So this is the Riemann curvature tensor. Riemann Christoffel curvature tensor will call. From this RABCD, we constructed actually a rank 2 tensor, what we call a, let's say, RAB. Okay, so that is known as the Ricci tensor. Okay, so then we constructed the Einstein tensor, let's say the GAB. Okay, so that is something RAB minus half of GAB R, where R is known as the Ricci scale. Okay, so we can construct the R from just contracting both indices. So you that means just taking the trace of this RAB. So okay, RAB can be constructed from this Riemann curvature tensor, just contracting the upper and one lower index. Okay, in other words, taking the trace of this RABCD. Okay, so this is how we do it. Huh? So these are the tensors what we have already at hand. Okay, let's forget about for the time being. Okay, what is their structure? Okay, so let's go to the Einstein's suggestion. Okay, so what is the Einstein's suggestion? Gravitation is the manifestation of curvature of space-time. Clear? So in other words, that means the curvature of the space-time gives us the gravity. Okay, so that curvature of the space-time is induced by the distribution of the matter and radiation. Clear? So let me write it. So we are having this thing. This is the idea, profound idea. Gravity is a manifestation. Space-time curvature. Okay, induced by the presence of the matter. So when I say the matter, it means radiation as well, because there is an equivalence of matter and radiation. Okay. So therefore, we must write a set of equations that will govern the two things. Is it? Okay. Now tell me when I. Okay. So when I am having the curvature, space-time curvature. Okay. So that we need to figure out which is the suitable quantity which will describe our space-time curvature. Clear? Okay. So it means, let's say if I am writing, okay, so let's think it this way. You are having Maxwell's equation of motion. So if you are having Maxwell's equation, is it? So they describe the field equations for the electromagnetic field. So let's take the inhomogeneous Maxwell's equation for the time being. Okay. So what you are having those equations, you are having charges and currents on one side of the equation. They produce the electric and magnetic fields on the other side. Clear? So in other words, the electric and magnetic fields are produced by the charges and currents. Clear? Okay. So now here I am saying you are having the curvature. That's actually the geometrical property that is produced by what? The distribution of the matter or the presence of the matter. Is it? So I need to figure out a quantity which will describe me what? Which will simply describe me the matter or the radiation. Okay, so a quantity that this, okay, so it should have, okay, so it should have what kind of properties? It should give me actually the energy of the matter. So the quantity that will describe me the distribution of the matter or that will specify me the properties of the matter, it should have, okay, it should give me the concept of the energy density, okay, or it should give me the energy, it should give me the momentum, and it should give me actually the stress as well, because let's say when you compress the matter or when you relax it, okay, so what will happen? So there is some sort of stress arising in the matter. Is it clear? So or in other words, there is actually the flux of the momentum, I mean crossing a certain boundary, okay, which represents the, okay, or which encloses the matter. समझ रहे हो? A quantity that describes, I mean, all these properties like the energy, momentum, stress, and so on. We call that as an energy momentum tensor. Okay, so this we have already known. So I'm having the energy momentum tensor, which characterizes your matter or radiation simply. Okay. Okay, so energy momentum tensor. So let's call that energy momentum tensor. It's a rank 2 symmetric tensor. Okay, so let's call it as a T mu. Samashivan? So 0, 0 element, let me write it as T00. So it gives me the energy density. So it is very important. This we have already figured out. I mean, in electrodynamics course, when we were dealing with the energy momentum tensor of the electromagnetic field. Okay? So if you remember, so the electromagnetic field has, certain quantities which you can calculate from this energy momentum tensor. First is what is the energy density present in the fields. Okay? And second is the flow of the energy across a given surface, that we call the pointing vector, is it? Or in other words, the pointing vector gives you the momentum transfer across a boundary. When an electromagnetic wave passes, so you are actually carrying actually what? The momentum. Samashaman? So you are having the pointing vector also carried in what? This energy momentum tensor for the electromagnetic field. Now when you are having the momentum transfer across the surface, so it will create actually stress in that very surface, is it? Samashaman? So you are having the Maxwell's tensor also included. We simply represent the stress in the electromagnetic field that is actually incorporated in the energy momentum tensor. Similarly, let's say if you are having gas of the particles, okay, a gas, we call it as a dust. Let's say a sphere, you are having a sphere carrying a gas, non-interacting particles, clear? We call that kind of sphere as a dust. In cosmological terms, we call it as a dust sphere, okay? Dust sphere does not mean what? The dust in the usual sense. It is simply the gas of non-interacting particles. Now let's say I have to construct an energy momentum tensor for that, okay? Or let's say how I describe the energy momentum tensor for that dust, okay? Dust sphere. So first thing, I should get actually the correct energy density, is it? So it should represent what is the amount of energy present in that, in that sphere, or the total amount of energy which the molecules of that sphere represent, okay? So, and second thing, the molecules are moving, is it? So what that means? So it also carries the momentum. Samashaman? And one more thing, so if you take a given point at a given location, you will be having molecules moving in the arbitrary direction. Let's say along x direction or along y direction. What does that mean? Let's think of, okay, so let's think of a cube, a rubber sheet. So let's say like this thing, okay? So at a given point, so let's say you are having something, a particle either moving along this direction or this direction. What it will create? It will create actually stress in that very thing. So shear and stress will arise where? In this very rubber band. So in other words, at a given point in that in that dust, so you will be having what? A stress as well. So that means the energy momentum tensor, when you write for, let's say, the gas, this dust sphere, so it should give me what? One of the components of the energy momentum tensor should give me the energy of the particle, or the energy of the sphere, or the energy density of the sphere, I should say. Another certain component should give me actually the momentum. Okay, you choose, let's say, certain boundary, let's say. So you can call what is the momentum transfer across this very boundary, is it? So, or in other words, what is the momentum carried by the particles? It should be also represented by this thing, okay? And it should also represent me what? Stress. That is why we call this T mu energy momentum stress tensor, okay? So we'll call only the energy momentum tensor. Okay, let's say for the gas molecules here, so this T mu, let's say rho is the mass density, okay? Let's assume rho is the mass density of the gas inside this very volume V, let's say. So let's assume u is the velocity, okay, for velocity vector. So you can put it like this. So now We write it as a contracurrent. Okay, so this will represent to me what? What it will represent to me? Energy momentum tensor. Okay, so it can be figured out easily. So let's take this very example. Why I am taking this thing, you will see in a moment. Now let's take 0 element of this thing. You don't need to derive it. Just let's argue for this. It's a correct energy momentum tensor representing a sphere of non-interacting particles or a dust sphere. Clear? So let's take the 0 element. So what it gives me? Rho u0 u0. So what is u0? It is 0 component of the 4 velocity vector. Okay. So let me write that. Okay. So if you remember u mu, sorry. Okay, I have used here mu as a 4 index. So in a moment I will change it. So it's like this: 1 minus v square by c square. Okay, then you are having v divided by root of 1 minus v square by c square kind of. Is it? So this is okay. So now let me tell. Okay, so what is t00? It is rho. So let's say v is small for the time being. Let's say we are where? V is small. Okay. Should it be c here? Can it? It should be c. Yeah. So it is actually c probably. Okay. Yes, it is c. So what it is? Let me write. It is c square divided by root of 1 minus v square by c square. Okay. So in a moment you will see it. Let's say v is very small. V by c is less than 1. Okay. Non-relative limit. So what does it mean? So it is simply rho c square. What it is? Rho is actually the mass density. So mass into c is what? C square. It's energy. So it simply gives me what? Energy density. So this means actually this represents actually the energy density of a relativistic gas, because we are in the relativistic domain here. So now let's take that T0I. So what it gives me? Rho U0 and Ui. Okay. So let's take in the non-relative limit V by C is less than 1. So V by C is less than 1. Okay. So it is rho. So this is equal to 1. Okay, because U0 will be actually, sorry, C. It is something. What is Ui? So it will be something V. So what that is? Rho C times V. What it gives me? It is actually the momentum density. So what is the momentum density? That if you see in terms of the field variable, it's actually the pointing vector. Isha? Because the pointing vector represents what? The momentum density. Here we don't call it as a pointing vector. It is simply what? The momentum density. So similarly, if I now let's write Tij. I mean ijth component. What it gives me? Rho Vi Vi. Is it? So Ui will be Vi. Ui will be what? Vi. So what it is? It is simply the mass density. It simply gives me the distribution of the velocities at a given point. Is it? So it means the particle is moving. Let's say I is x, j is y. So what it gives me? Vx and Vy. So it is actually the velocity along x direction and velocity along y direction. What does that mean? It's actually the stress. So that means you can see this actually correctly represents your energy momentum tensor for what? The dust sphere. Got it? Have you got the idea what the energy tensor means? So now here we have included only the dust sphere, but it can also happen you are having the radiation field as well. Let's say you are having a dust sphere and then you are having the electromagnetic field. Let me take this kind of, let's think of sun. Okay, sun is a star. It's a spherical object for us. Okay, so let's think inside the sun you are having the gas molecules. They are all non-interacting. So I can think it as simply a dust sphere for the time being. So the energy momentum tensor will be that. But there is also an electromagnetic radiation. So you need to put the energy momentum tensor for what? Radiation as well. So that means I should put actually there's another term here. So that means the energy moment, when I say it, I am having the presence of the matter, it means the radiation as well. That means I need to take into account the energy momentum tensor for the matter as well as the radiation if both the things are present. Clear? Okay, now look here. Everybody is clear? Okay, good. So what I am saying on the so I am having like this. You are having the curvature on the, let's say, curvature on the left hand side. It should be proportional to what? Energy momentum tensor. So much on. So what is on the left hand right hand side? A rank 2 tensor, a symmetric rank 2 tensor. Clear? So that means on the left hand side I should also have what? A rank 2 tensor which should specify me the curvature. So much on. And that is actually the Einstein curvature, most general form. So in other words, I am writing this as the equation minus half r, let's say g mu nu r. So this is equal to actually 8 pi g by c raised power 4. The constant of proportionality you can take. It's like this. We call this as Einstein's field equation. You are having the curvature on this very side. You can derive it. There is no. So I am not deriving it at all because it will complicate things. So I am just giving an argument. You are having a geometry on the left hand side and the what? Matter on the other side. So the matter dictates the geometry how to behave, and the geometry dictates matter how to curve. Okay? So much of how to move, rather I should say. Got it? Okay. G is the Newton's constant of the gravitation. So much of these are known as the gravitational field equations. Okay? Just like you are having the Maxwell's equation, or you can say these are the Einstein's equation. These are the equations which were proposed by Einstein. It was actually later. These are all. This is actually intuitive idea of the Einstein. Okay, curvature is equal to the this kind of idea. Okay, so based on that intuition, he led this kind of form. Actually, in the earlier description, this term was not there. Okay, it was only this term, but later on. So this was okay. It was put there to have the constant equation. Okay. Now the point is that how to derive it. It was actually later on Hilbert who proposed an action, a gravitational action from which we can derive what these field equations. So let me give an idea. So, but I will not derive them here. Okay, because it is completely basic course. That's why we will not go into those technical details. So the gravitational action that was proposed by Hilbert is like this thing. Let's say in 4-dimensional space-time, it's this root of minus g. This is actually the Jacobian, because now this is actually, this entire object is invariant under arbitrary coordinate transformation. That's why you need to put root of minus g. So then you are having this Ricci scalar. Okay, because this action has to be a scalar quantity. Ricci scalar is a quantity which is invariant under, which is a scalar under any general coordinate transformation. Okay, so this will define me only the gravity. Now you can put also a Lagrangian. Okay, so like this thing, Lagrangian for the matter. So so this, when you vary it, so let me write it like this thing. So let me write it. Okay, so let's put it this way. Okay, so let's try. So Lagrangian over matter. Right? Okay, so let's forget about matter is not there. Let's say matter is not there, so this term is not there. Clear? So if you vary action only with respect to this object, you will get this side is equal to 0. Samajha? But if you consider matter as well, okay, then that will generate this energy momentum tensor. Got it? Let's rewrite this very equation. Any question? If you have any question till now, just tell me. Yes? No questions? Okay, so have you got the idea? So the action principle is what? Delta S is equal to 0. Then we need to do actually the variation of this very object and variation of this very object. So it will yield me exactly this kind of equation. Samajha? So let's rewrite this very equation, which is useful to us. Okay, so this constant, can you tell me how we fix this constant? So how we fix this constant? Just getting the Newtonian limit of this very equation, you can fix the constant. समझ आवा? Okay. So let's say you put some constant k here. You don't know what is the value of the constant. How you can do it? How you can do it? You figure, because the Einstein equations of gravitation are generalizes the Newton's law of gravitation, is it? So that means when I take the Newtonian limit, so it should reduce to where? Newton's law of gravity, is it? So in that way you can fix out this constant. Clear? Okay. So there is one more point. When Einstein tried to look at the solution of his equations, he introduced a constant, what we call the cosmological constant. Okay? I will not tell anything about cosmological constant. Okay? समझ आओ? Because it will hamper our later discussion. At the end of the course, I will. Yes.
So if it would be equal to 0, that's not very clear.
So
then what would it say?
Yes, that's I'm going to say. Okay? T mu nu, if I put equal to 0, so in a moment I will tell you what exactly it means. Okay? So let's rewrite first them. Okay? Let's rewrite it. These are the only equations we will use in the tensorial notation. Then rest of the things we don't have to do any kind of tensor analysis. Okay? So we will do the simple mathematics. So only this. So what I will do, so I can write this equation like R mu nu. Can I write it? Just raise one of the indices. So you can put like this: G mu nu R is equal to 8 pi G by C raised to 4 P mu. Can I write it? Okay, raising one of the index up. Okay, throughout the equation. So it is the same thing. So now let's contract. Okay, contract the indices. So there are only two indices. We can contract them. Okay, contract mu nu. So implies we are taking trace. Implying taking trace of this equation. Okay, so what it means? So let's put, when I contract mu and nu, so it means I put mu and nu same. So it is something like R mu mu. So this is now the contraction. So half of G mu nu. Let me write for the time being. It is G mu nu mu. So it is 8 pi G by C raised to 4 P. Okay. Okay. So can anyone tell me what this G mu is? It is simply a 4-dimensional this Kronecker delta function. Okay. So what it means actually? This R mu mu. Can anyone tell me what it means? It's something like, okay, so let's say if I am having A mu mu. So it means actually A00 plus A11 plus A22 plus A33. So that means that's why we call it as a trace. It is the sum of the diagonal terms. Got it? So समझो this. I have used mu nu. So we should. Okay. So here mu nu means where from? 0 to 3. Okay, just remember. Because the notation we are using ij, we are using what? From 0 to 3. Mu nu alpha beta we are using from 1 to 3. Okay. So here you should know mu nu goes from 0, 1 to 3. I should have mentioned because I don't know. Okay, so this G mu mu, this is actually delta mu mu. Okay? So समझ आओ? Can you tell me what this delta mu mu means? So it means delta 0 plus delta 1 1 plus delta 2 2 plus delta 3 3. How much is that? 4. This is 1 1 1. It is equal to 4. Trace, it simply gives me the trace of delta function. It is 4. So what you get? So you get R mu mu. Can you tell me what this object is? Both indices are contracted. So it's now a number, is it? RS scale, it is a function, is it? It's a scalar function. What is that called? Simply Ricci scalar. What is Ricci scalar? So you are having Ricci scalar like this in GAB, RAB. Both indices are contracted, is it? So it is same thing what? RAA, you can say. Clear? So समझ आओ? So what this is? It is equal to R minus 4 by 2R that's equal to 8 pi g c raised power 4. T mu mu I will call as a t. Okay, here I have defined a t as, because it is simply as a scalar quantity. It is the trace of the energy momentum tensor. Now you will see actually the simplest of way to figure out the Ricci scalar. Okay, if you know the energy momentum tensor, you can figure out what? Ricci scalar. Okay, so this is half, so it means, so it's my R is equal to minus 8 pi g by c raised power 4t. Okay, so this is the relation between what? Ricci scalar and energy momentum tensor. So if you know the energy momentum tensor, what you need to take? Trace. So समझ आओ? Got it? So let's take, so in the example we have considered for the dust sphere, what is our T mu nu? For the dust sphere we wrote like this. Clear? So what it gives me? T mu mu. Anybody? So it is rho u mu u mu. So what is that equal to? So anybody can you tell me what this object is? It's 1 or minus 1. But velocity is a time-like vector. So what is the value? It's minus 1. So it's minus 1. So that is Ricci scalar is 8 pi g by c raised power 4 times rho. So in this case, R is simply equal to what? 8 pi g by c raised power 4. Okay? So this is actually the value of R. Okay, so now let's substitute back it in the Einstein's equations. Okay? So this is equal to actually minus 1. Because it is simply the dot product of what? 4 velocity vector. Okay? And that dot product is minus 1 for the time-like vectors. Velocity is a time-like vector. Okay? Got it? So let's rewrite it. Therefore, we have this R mu nu minus half G mu nu. What is R? So it is like this minus. So it will be simply plus now. 8 pi G by c raised power 4 T is equal to 8 pi G by c raised power 4 T. So which implies therefore what this R mu. So this is the okay. So this is how we write now the Einstein's equations. So it's 8 pi g by c raised power 4. It is T mu nu minus half of g mu nu. Okay, so now let me come to the question of that. Okay. Okay. So now let's say our T mu nu is 0. What does that mean? There is no matter present. So when this situation arises, okay. So so let's say we are solving these equations for sun or some spherical star for the time being. Clear? Let's say for some star we are solving it. Okay. So I am having a star. So the matter distribution is inside the star, and I will forget about the radiation emitted by this very star for the time being. Clear? So tell me if I am solving Einstein's equation at this point P. Clear? So does there exist any matter at point P? So let's say I am solving and these equations where? At point P, which is far away from this very source. Let's say forget about we are on the earth. Let's say we are in the space and we are far away from the sun. Clear? And we are trying to figure out here, let's say, the solution of the Einstein's equation. Clear? Just tell me, is there any matter, for what matter distribution we are trying to solve? The matter distribution of the sun. Clear? Is that distribution existing here? No. So that means it's an empty space. Here at this very point, then I can say, or this very region, I can say it's an empty space where there is no matter and radiation. We are not considering radiation here. So I am saying there is no matter and radiation. When you don't have the matter and radiation, what you are having there? This T mu nu is 0. So it means this T is also 0 because it is the trace of the T. Clear? So in that very case, the right hand side is what? 0. So you are having only R mu nu is equal to 0. So the Einstein's, we call this equation. So when we have when, okay, so in presence of no okay, so with no matter distribution, with no matter distribution, okay, this T mu nu is equal to 0. So we are having vacuum, we call it as a vacuum, classical vacuum, okay, classically thinking, okay, not the quantum mechanical, vacuum or empty space, Einstein's field equations, okay. So in that very case, this R mu is equal to 0. Samajh? So think of, okay, so now if I have to, let's think of an orbit around the sun. What is the equation I will solve? I need to figure out what is the orbit of Earth around the sun. Actually, I am solving Einstein's equation in presence of the sun, correct? And ignoring the field of the Earth, is it? So what I have to solve then? So this Earth is actually in the empty space around the sun. Because we are not considering the gravity due to Earth. We are considering only gravity due to what? Or the curvature due to the matter distribution of the sun, or the curvature induced by the sun itself. Okay, we are moving in that very curvature. So for that matter, what we need to solve? This very equation, empty field equation. Got it?
That would mean the space is flat.
No, it's not. Your having curvature is produced. Okay, so this is the curvature due to the source itself. Clear? In which we are trying to figure out our solution. Think of the Maxwell's equation. So Maxwell's equation, you are having the solution without rho and j, without current and the charge, is it? So what those equations? So that means you are having a vacuum existing for the electromagnetic field, is it? Or the electromagnetic wave. So what is that? So you are having simple plain electromagnetic wave arising from the vacuum, is it? Samajh hai? So that means a source free region. Similarly here it is what? You are, although you are having the source of matter somewhere, but you are far away from that very matter and trying to figure out what could be my orbit. So this is actually the curve. Let's think of a sun. This will be simply what? Curvature produced by the sun, and you are moving in that very curvature. Samajh aaya? So now if I am saying, let's say if I take into account, let's take Earth as well. Let me think of the gravitational field of the Earth. So you are having the matter present as well. So that you need to put something corresponding to that very matter. Samajh? Got it? So think of a, let's say you are having some gas, dust sphere. It tries to form a star, okay? And an observer, let's say if an observer is outside that very dust sphere, okay? So he will have to look at these kind of equations. But if this observer, let's say it is at one of the particles in that very dust sphere, if that particle is within that very sphere, clear? So what he will see? He will see actually the energy due to the matter distribution as well, clear? So then he has to put this side as well. So it's very, because when we think of the vacuum, we always think vacuum related to electromagnetic field, clear? So it's a vacuum with respect to what? You don't have actually the matter distribution or the radiation, or you don't have the matter or radiation present. Okay? So it's a vacuum defined for the curvature. It's a geometrical concept, you can see. Okay? Any problem? Okay, so now let's look at this thing. How many equations are there? Okay, so you are having the Newton's gravity is a static theory. It contains only one equation of motion. Okay, so what is that equation motion? Newton's gravity, it is lambda square phi is equal to 4 pi g rho, is it? So Poisson equation, this describes your Newton's gravity. Okay, you are having a source here, and this source produces what? The potential itself, correct? Okay, so you can argue for why we need an energy momentum tensor there. You can argue from here this equation as well. Suppose this rho is the source for phi, is it? But this, by the new Einstein's postulate, this phi is also the source of what? Rho, correct? So that means you require, more terms on the right hand side. So which will describe actually the dynamics of this rho and so on, correct? So that's embedded in where? The energy momentum tensor. Okay, let's forget those things. So you are having only one equation from the Newton's law of gravitation. Now how many there are? So if you see this energy momentum tensor, it's okay. Forget. So this G mu is a symmetric tensor, clear? So rank 2 symmetric tensor. How many independent components it is having? 10 components, clear? So rank 2 tensor, which is symmetric in nature, it's having always what? 10 independent components in 4-dimensional space-time, clear? समझ आवा? So that what is the rank on this side? 2. Rank on this side is 2. So that means the number of components which I am having here are same as here, clear? So this is a rank 2 tensor, symmetric in nature. So it means how many components you are having? 10 components in 4-dimensional space-time. That means how many equations I am having? 10 equations at hand, clear? So that means these are actually how many equations? 10 equations. Okay? So instead of having one equation, you are having how many? 10 equations in 4-dimensional space-time. Let's say if it is many dimensions, so the equations will grow, clear? So furthermore, it's actually a non-linear equation. Non-linear in a sense what? How we define linearity? Let's say if I am taking solution 1 and solution 2, take their superposition, let's say sum of those two solutions, it is also a solution of an equation. Let's take the Newton's laws, or let's say any differential operator. Okay, you take y1 and y2 are the solutions, and the sum of those are also as a solution. That we call a linear superposition. Now it is not true here. Okay, because this R mu contains derivative. Okay, it contains derivative of the Christoffel symbols, and Christoffel symbols also contains what? Derivatives of G. Is it? It is the double derivative of G. Clear? And because of that, the structure itself, it's actually, it does not obey the linearity principle. The sum of two solutions is not what? A solution. Simple. Clear? Got it? Okay. If you have any question? Okay, so let's move ahead. Let's figure out the non-relative limit of this equation. Let's figure out the Newtonian limit. So let's begin with this. Okay. Now tell me which component is suitable for Newtonian limit. Can anyone tell me? So look at this very equation carefully. So what are the components at hand? So you are having, let's say, you are having R00, correct? Then you are having R01, R02, R03. Then what you are having? Okay, R11, R12, R13. Then you are having R22. Then you are having R21. It is here. Okay. So R22. Then what you are having? R23. Then you are having R33. Then you are having 32 is here. So all the 10 components are there. Clear? Now tell me out of these. So this is the time. 00 means time component. Clear? So out of these things, just guess which component of this very equation can give me what? Newton's equation. Which component can give? Just guess. Okay, just tell me, when we are taking Newtonian limit, we are saying gravity is weak, is it? At certain point the gravity is weak, so that we can approximate our metric tensor as a Minkowski space metric plus some correction. What we have done in what? The geodesic equation. Clear? Yacha? Okay. So now tell me which can give me this thing. Since Newton's equations are static in nature, is it? So the static concept comes from where? Time dependence. If something is time independent, that means it is what? Static. Clear? So the first point which can give us is this actually R00. So because it contains the time component, so that means the staticness should come from R00. Now if you see why, uh, since this R contains the derivatives of metric tensor, is it? So much ever? It contains derivatives of Christoffel symbols, and Christoffel symbols contain derivatives of the metric tensor. Okay, when I take the 0 component, it means I am actually taking time derivatives of what? The metric tensor. And if metric tensor is, let's say, gravity is v, metric tensor is just what? The Minkowski space metric, then the time derivative of that is what? 0. Or in other words, the time derivative of the metric tensor itself is 0. So in other words, the static limit should come from where? 0 component. समझ आओ? Okay, so let's take it. First, let's write what this R nu is. So let's write. Can anyone tell me what is the formula for this? So let me write. Okay. What is our R A B? So I have settled used R. Okay. So R A B is defined like this in R A B C. Okay, just the contraction of pair of indices from this thing. Now let's write this tensor RD ABC, the Riemann tensor, which is defined like partial B gamma DAC minus partial C. Just check the indices. So I will. So this I have taught earlier how to do it. EB minus gamma E, EB gamma B is. Okay? So now tell me what our RAB is. Anybody? So you need to contract A and, okay. So this D and B. So that means you put D and A same. Okay? So what that is? Partial B gamma A AC. Now it is a contracted index, partial C gamma A B plus gamma E A C gamma A E B. D is contracted. A and B you have to put as same. So gamma E A B gamma A E C. Clear? समझ आओ? So this is what we have at hand. Okay. So now, so this was the definition. So this I will try. Okay. So let me take. Okay. So in order to figure out, so what we need, so we need R00 component. समझ आओ? For the Newtonian limit, what I need? R00 component of this very equation. That means we need to solve this very equation. R00 is equal to 8 by G by C raised to 4 T00 minus half of G00 and T. Clear? So, so and what we will use, so we use our G nu approximately equal to eta mu plus some h mu, where magnitude of this h is less than 1. It's very small. So this is our weak field approximation. Now let's take R00. Let's take R00 from here, from this very equation. Okay, now let's take R00. So therefore, I require this equation. That's why I have. Okay, so I don't require that because I have already written. So let's take R00. What is this R00? Can anyone tell me? So put A and B, put B, it is not, it is C. Because A is a contracted index, it is B. Now like It's BC. A is a contracted index. So what is that equal to? Put B and C as 0. So it's partial 0, gamma A is 0 minus partial 0, gamma A. So some gadwad is here. So it should be something A, it should be equal to CP. It should be A. Probably. Is it? Yes, it should be something. Yes, it is true. Okay? It should be E. It should be E. Just check your formulas correct. Carefully. It should be E. Plus gamma E A 0, gamma gamma A E 0. Okay, so just we are done. Don't get after that. So gamma A. So A is there. B is 0. Is 0. Again, there is some problem. Okay, so it has to be equal to BC. So A. Okay, so it is something. So it has to be equal to BC. This has to be equal to B. 0, 0. Just check your formulas. Now look here. So point is here. Just look at this very formula. It is very simple. Okay, we don't need to evaluate it explicitly. There is no need to put it explicitly. What we are ignoring in our Newtonian limit, we are ignoring order of h square terms. Is it? So order of h square terms are what? Ignored. Okay, is that true? Because h is very small, h square is very very small. Correct? Now let's look at this very thing. Look at this very objective. This gamma contains what? Derivative of g, is it? Tisha, does gamma contain derivative of g? And okay, so let's say gamma contains derivative of g. So this means derivative. Okay. So but g we are approximate at as a constant. Eta is a constant. So it's something eta plus h. Clear? And this is equal to 0. So it is simply of the order of what? Partial h. Clear? So in other words, this object is order of h. Clear? And this term is also order of h. Actually, it's more than h, but we'll simply approximate it as the order of h, and this is order of h. So what is the order of these two? This product. So this product is actually order of h square. Samajh aao? What is the order of this thing as well? So this is also what? Order of h square. So we are ignoring h square terms. So that means we can safely ignore these two terms. Samajh aao? Okay. So we can ignore the last two terms. Last two terms are because of this very fact. Now let's look at the first term. Okay, what is the first term? Partial 0, gamma A is 0. Clear? So now what this gamma contains? It contains derivative of g, is it? Okay, and you are having the time derivative of g. Since we are looking at the static limit of the Einstein's equation, clear? So it means, okay, what we are saying. So this is the first point. The second point is what? Static limit, clear? What is the static limit? So the partial 0 of g that's equal to 0. Our matrix is actually static. If you see, it's actually the consequence of this thing. Let's take the time derivative of this thing. So I'm saying it is static in time. So this will be a function of coordinate only. Samajh? So it will be equal to 0. Got it? So that means this term is also 0. By the static term, this is equal to 0. Now what remains there? What remains there? So you are having only one term now. So therefore, this R00 is approximately roughly equal to minus partial A gamma A 0 0. Clear? तो समझ आओ. So now A goes from 0 to 3. समझ आओ? Is that true? So what I can write it? So this I can write minus partial 0 gamma A 0 0, then minus partial I gamma I 0 0. What this object is? It is 0. It's again by the static limit. This is what? 0. So that means our R 0 0 is equal to minus partial I gamma I 0 0. Okay? Okay, so now let's go to what we have done in the this limit. When we are doing the Newtonian limit of the geodesic equation, what was this gamma I 0? Okay, so from geodesic calculation, from Newtonian limit of geodesic equation, we have calculated this gamma I 0 0. So what is that equal to? So here I means, okay, so I is running from 1 to 3. I will mention it. Yeah? Here it runs from 1 to 3. So can anyone tell me? Oh, when you when you, so it's equal to minus half R. When you, gamma I and Isha? Oh, Isha? So this is what we have got it. So that is minus half of gradient of S0. Clear? So let's write it for the time. So what is our S0 0? This we have identified in that very case. So this is very important approximation. So now let's substitute it here. So what you get? So which implies our R0 0 is roughly equal to minus, okay, minus and minus is plus, so it is half of partial I, then x0 0 is actually 2 pi 1 plus 2 pi by c square. What is that equal to? If you see, this is Laplacian, Nebula square, so this is simply equal to 1 by c square Nebula square. So that's our R0 0. So much more? It is Laplacian of phi. Okay, so now let's go to the right hand side. What was the right hand side equation? What is our right hand side equation? So that's equal to 8 pi g by c raised power 4 t0 0 minus half of g0 0. Clear? So this very side will depend upon how you choose this energy momentum tensor. That will give me what is the kind of matter distribution you are looking at. Samajh? Whether you are looking entirely at the radiation, you are entirely looking at, let's say, this dust sphere or something else. Clear? Samajh? It will simply depend on that. If you look at this very form, okay, so let's go to this T. So let's assume our T mu nu, that's equal to rho u mu u nu. Okay, so this is for the dust sphere. So this is our RHS. Samajh aaya? So now what is our T00? So it's simply equal to rho c square. Just I have shown you. Now what will be now this T? P is equal to actually T mu mu. So that's equal to minus rho. Samajh aaya? Minus rho I can make it. No, it should be c square. Okay, so this u mu is actually equal to minus c square. Because 1 it will be when c is equal to 1. It's like this. So u is there minus c square, because that 1 we are using to c equal to 1. So now let's look at this very objective, what it will be. So it is 8 pi g by c raised power 4. What this object is? T00. It's rho c square. So it's plus. What is G00? What is G00? minus 1. So you are having rho minus, then you are having half rho g 0 0 is minus 1, t is equal to minus rho c square. Okay, so how much is that equal to? So it's equal to 8 pi g by c raised power 4. How much is that? It is half of minus, so it is half of rho c square. Clear? Tisha? Yes. Is it clear? We have actually missed a factor of 4, a factor of 2 somewhere. Okay, so let's check it. What it is equal to? So it is equal to 4 pi g rho by c square. So therefore, r00 is equal to like this thing. You are having 1 by c square, nebula square phi. That's equal to 4 pi g rho by c square. Oh no, there is no. Yes, it's correct. This cancels with this thing. What you are having? What this is? Clear? Is it true? First tell me, is this true? Huh? So what we have got? Newton's equation. Now what we have done? Okay. So here I have taken a dust cipher for which this T mu nu is rho mu nu. It's not necessary to take this thing. You can take, let's say, the electromagnetic field. Okay. For that you can assume what this T00. If you see essentially this T00 minus half, it's actually the this very object. Since what this, okay, so let me tell you what this T00 represents for a electromagnetic, general of this energy momentum tensor. T00 represents always energy density of the particle, clear, or the energy density of the field whatsoever you are having. So you are having an energy density. What you will add? Tell me what you will add. You will add an energy density. So if you see you are having an energy density minus half of an energy density, clear? So what it will give me? Half of the energy density. So that means this very object is half of energy density. Samajh aaya? So what you got? Now tell me in the general case. So everybody got this thing? Now you cannot add momentum density to the energy density. What you need to add? Energy density and energy density. This object is an energy density. Okay, so it is simply equal to this. So it will be simply 4 pi g by c raised power 4. Energy density is how much? So let's specify if you are having the matter carrying the mass density rho. Okay, what you need to multiply so that you get energy density? C square. So this energy density will be simply rho into c square. So this gives you what? Energy density. So this c square and c raised power 4 cancels. What you get? 4 pi g by c square rho. Clear? And you are having 1 by c square here. So this will cancel. Got it? Samajh aaya? Instead of specifically choosing, let's say, the dust cipher, you can do it by this way. Clear? Any problem? Has everybody understood this non-relative limit? This is very important. Okay? Okay, so let's stop then.